In this video, we're going to discuss the equilibrium of a particle and do some example problems related to that. Before we do that, we need to go over a tiny bit of theory, but don't get hung up on it. Just make a few notes and then get right into these examples. So first, before we do problems concerning the equilibrium of a particle, and also I should mention that this is in 2D, we want to know the definition of equilibrium. What is equilibrium? What do we mean by a particle? So firstly, let's talk about what is the equilibrium of a particle. Well, a particle is just a point in space, and we want to imagine that in the xy plane because we're going to be doing everything in 2D. So it's just a point in space, and for that particle to be in equilibrium, it needs to remain at rest if originally at rest, or remain at constant velocity if originally at constant velocity. Basically, it doesn't change throughout the question. It's just, and in this case, everything's just going to be still. There's nothing to do with constant velocity. In this case, it's going to just remain at rest. But that doesn't mean that there's nothing acting upon the particle. That just means the forces acting upon the particle are equal in each direction. The sum of x forces equal to 0, and the sum of the forces in the y direction also equal to 0. And that is a useful hint when solving problems. That's how you solve these problems. You need to know that since this particle is in equilibrium, the forces in each direction sum up to 0, because that's how you're going to solve for some forces that you don't know, some unknowns. Next, I want to talk about the problem-solving approach for these types of questions. So it's pretty straightforward, and it's very similar for each question. So doing a lot of practice will extremely benefit you. But let's just say we have a particle, and there's a bunch of forces acting upon it. You know from your prior mechanics courses that to do this effectively, to find the unknown forces, you need to draw a free body diagram. So number one, free body diagram. Now I like to draw my free body diagrams like this, where it's just, I do the x and the y axis, and I draw the forces acting upon it. But some people like to do them differently. Some people like to draw one for the y-axis, one for the x-axis. It's really up to you how to do it, whatever benefits you, but you have to do it. Trust me, it's very good practice to do, and when these questions start having 5 or 6 different unknowns, sorry, not 5 or 6 different unknowns, but 5 or 6 different forces acting upon a particle, it's very helpful to have a free body diagram. Next, you're going to want to do like pretty basic vector additions. And you're going to do that by writing out the equilibrium equations. I'm going to call them EE. Writing out the equilibrium equations. Now, what is the equilibrium? What are the equilibrium equations? The equilibrium equations are just what I showed you earlier. The sum of forces in the x equals to 0. We call them the equilibrium equations because all of the forces add up to 0, right? And you're just going to want to do this for both directions. Since it's 2D, it's just the x and the y direction. So basically, it's going to look something like this. You're going to do it you're going to draw your free body diagram. You're going to do the sum of x forces equals to 0. You're going to say 0 is equal to, we have force 1 in the x, force 2 in the x, etc. And then same thing for y. I kind of drew that differently, but yeah, and we're just going to do the same thing for y. Next, you need to break up any forces that appear in both planes, appear on both axes into components. So let's go back to our free body diagram right here, and we see that force 1 is on the x and y plane. It has an x and y component, and we know how to do this with basic trigonometry and vector addition, right? Stuff you've learned in prior classes. But if you don't know how to do this, please touch up on it because it's the basis of this course. So we'll usually have a force, maybe given a magnitude, maybe given an angle right here. But anyway, we need to use basic trig to find the y component and the x component for F1. And once we do that, we add it into our equilibrium equation. And obviously, if we have a force that, I'm going to use blue for this. Obviously, if we have a force that goes along just one axis, it doesn't have components. Like this force right here, we'll call it F2. It only has a y component, so we're not going to break it up into components because there isn't an x component. So we're just going to add it straight to our equilibrium equation for the y. And that's basically it. Once you have your equilibrium equations and you broke up everything into components, you just do algebra and solve for your missing variable. There is a few things I want to talk about first before we do some problems, and that is some of the language you might see and some of the equations you're going to have to use. So in a lot of these problems, you're going to see something hanging from a ceiling, hanging off a wall, whatever. It's going to be a mass, say a box, and it's going to be hanging from the ceiling. And it's going to be hanging by some cables or rope. And as you know, a rope is in tension. It's always pulling. You cannot push down on a rope. So there's no force pushing down on the object. The force is a pulling force that we call a tensile force that puts this rope in tension. So key takeaway, cables / ropes, anything pulling an object, they contribute pulling forces. Pulling forces, tensile forces, these all mean the same thing. We're just saying the rope is in tension. So in our free body diagram, this force would be going this way, towards the ceiling. The next thing that you're going to want to remember are all of the equations associated with the equilibrium equations, such as force is equal to mass times acceleration. I know everything's going to equal to 0, but you still need to know this. And that weight, the weight force from gravity, is the mass times the gravity, and gravity is 9.81 meters per second squared in these examples that I'm going to be doing. And this mass is just the weight, or sorry, this mass is the mass of the object in question. And just remember that even if we have an incline and our mass is on an incline and we want to find all of the forces acting upon it, and let's say it has a pulley and there's a rope going over this pulley. Sorry, that's a terrible rope. There's a rope going over this pulley. So that means it has a tension force going this way. It has, let's say it has an applied force going this way. It doesn't matter. Our weight force always acts straight down in the negative y direction. Doesn't matter the problem, it always acts straight down. So when you're doing the equilibrium equations and adding up all your forces, just remember that it's always acting straight down in the negative. It doesn't have an angle to it, is what I'm trying to say. But you can put your mass on a tilted axis, but then that changes everything, right? But for a normal XY plane, it's always going to act straight down. So in summary, A cable force or a rope or something that's suspending our object in question has a force that acts in the direction of the rope. It doesn't push towards the object because it creates a tensile force pulling the object. And weight acts straight downwards. And the weight is the mass times the gravity. Now that we know all the theory, we can get into any example involving the equilibrium of a particle with 2D x and y plane forces.